All right, spend some more time on GPUs today. I want to show an alternative to OpenCL. With OpenMP, lately, very recently, there's support for GPU targets as well. So I compiled a GCC from source with all the latest bells and whistles, and I'll take that for a spin and see how that works. First, I promised to resolve this mystery with the bug. We were running this program. This is the GPU find minimum index, and what it was doing is here we're running through first for each work item. We're computing a minimum over some chunk size. So that was I guess 256 elements or something that we just compressed into one minimum element. And then among those, we were saying for all these work items within the work group, let's find the minimum within the work group. And then that gets a little hairier because then we have up to 1024 work items all running concurrently. So to kind of merge all of those in a parallel fashion, we had this little loop here, which runs 10 times around to find the minimum among those 1024. For the first time, we run 512 work items in parallel. For the next time, we run 256, and so on. And eventually, in the 0th work item, we will know the minimum when it's running on its own. But the problem was, yeah, I think it was like that. Actually, it probably was the other one. So it looked like that. There was just a little bug in this. And so the reason that it worked for larger work items is just that this stupid test that we have, I put a -1 on index 18. That just happens to work with large enough chunk sizes. You get them in the right place, and you don't have to worry about this merging business because it's already at the 0th element. I think that's what happened. Okay, so anyway, this statement clearly has no effect. Well, I guess clearly it's a bit of an overstatement since it is a concurrent program. Mins could be volatile, in which case it would have an effect, but Mins is not volatile in this case. It's a local. Okay, so anyway, with this in place, everything works fine. But there is a whole lot of code just to find the minimum number, right? So it's this just for the kernel, and then this kind of to interface with the device and set up buffers, communicate back and forth. You know, much of this is boilerplate to kind of do the same thing, but it's still like a pain, right? It's a lot. So do we really want to go through all this trouble? Maybe, maybe not. I think it's nice that you can see exactly what's going on, but at the same time, you know, we don't write everything in assembly, even though then you can see exactly what's going on. There's some sort of trade-off necessary. So OpenMP offers a third alternative, and we've played with OpenMP in the past, right? But that was for multi-threading. So now multiple threads running on normal CPU cores, and there what it provides is an abstraction away from pthreads. Right? So you don't have to do a pthread create. You don't have to worry about splitting your data parallel program into multiple task parallel pieces, task parallel threads, and so on. So you got a lot of help from that. And the way OpenMP does this is sort of adding some annotations saying, oh yeah, I want to run this for loop, in particular loops. I want to run this loop in parallel. So run every iteration on a separate thread, let's say. And if that's if the programmer has already expressed this, then probably we can transform the program into something that runs on multiple cores, and sometimes buggy. The programmer may have to deal with race conditions, right? Having locks and having critical sections or barriers and so on. But at least we can get it to run on all these things, and something similar is true for the GPU. So I thought, why don't we look again at let's see. Oh, that's not it. Min. That's not it either. Let's see. To find the right program. Yeah, that's the one. Okay. It opened in another window. Let me try again. Okay, so now we're back to let me put the random number back in there. Now we are back to a sequential program. So that's what it looks like, both to generate the problem, right? Fill in all the random numbers, and then to measure and to find the minimum in this very large array. Same size, everything that we had before. It's only 4 lines, so that's nice. Like that's programmer time is also valuable. And if we compile this, it actually runs relatively quickly. So why don't we do that too? Let's see. Okay, ignore the extra parameters here. I'm just compiling, because we're not using offload at the moment, I'm just compiling with O3. It's a normal, completely normal compilation. And, okay, took 290,000 cycles. So let's say we think, 290 million cycles. Right? So let's say we think maybe this has potential for GPU programming. For running this loop on the GPU. It certainly looks pretty GPU-able. It's very parallel. There's only the question of the smallest here, but we've done that before with OpenMP. That's the reduction. Right? We can keep a local copy of smallest in the work item or in the individual iteration here. And then we can tell OpenMP that, okay, you have to combine all these values at the end before returning. Okay, so to do this, it's quite an incantation. So now I've compiled a GCC version that has support for NVPTX. That is the as far as I know, it's not the machine code of the NVIDIA GPU. It's an intermediate representation that is compiled by the driver into machine code that can then run on various different NVIDIA GPUs. So you can think of it as a sort of assembly. And in fact, the assembly does seem to get exposed. At least there's some way, I forgot how now, but you can actually see the assembly. It doesn't look like the x86 assembly, but it looks like a reasonable assembly. Okay, so as typical, we're saying compile this with OpenMP, but then we're saying, and also now we are targeting an offload, the GPU is one kind of offload platform. It could also be, Intel has this many core architecture. I forgot the name of it now. And there's potentially even FPGAs. There's all sorts of different ways that you could offload computation onto some other device, and this is sort of the interface for it. This particular GCC only supports NVIDIA PTX. Okay, so in fact I have a prepared incantation, I might as well use that. And that's the thing with OpenMP. It's these sort of magic incantations, and it produces an insane amount of code, and you don't quite know what it's doing. And it's really hard to figure it out too. The code isn't generated for you. Well, maybe there is a case. Maybe there is a way that we can get the sort of expansion of this pragma, maybe with a -e. You might get the preprocessor expansion of it. I haven't tried that. In any case, I find it quite opaque. Very challenging to figure out exactly what's going on. But I spent some time on this, so I think I can explain roughly what's happening here. So you've probably seen this before. Pragma OpenMP parallel 4. Right. So we can run that. And this will execute parts of this for loop on lots of different cores on the CPU. And then if you want, you can say, oh, reduction, mean smallest. So I didn't change the code here. I just put this pragma. So now we're saying, oh, let's compute a shared smallest value using the min as a reduction. So we take the smallest of all these smallests of all the various loop iterations. So far, so good. I think we've seen this before. We have some rough idea of how it works. You have these worker threads spinning up, and then there's queues for all of these work items, or the iterations around it, get queued up into some work queue. The worker threads pull one after another, finish that little piece of work, and then get another from the queue. We can even tell it like this. Okay, so here a work item in the queue is one iteration long. If we say 32, now it's 32 items in one iteration, just to kind of cut down on the overhead of distributing the work. Okay, in fact, OpenMP the compiler will try to pick something reasonable. All right. So now we want this to go and run on the GPU. It doesn't take that much more. You just run it on the GPU. It goes target, teams. So target says this code needs to run on a GPU. It doesn't run on the CPU. Teams is just sort of a prefix saying, oh, I'm going to tell you something about the coordination of the streaming multiprocessor stuff here, or the work groups. Right? There's another one that's called memory or something like that, where you say, oh, like I need this array to exist on the GPU, or that sort of thing. Okay, so let's see. So we're already pretty good, but so far we didn't tell it to do anything. If we say distribute, now it's going to take the parallel work here and run it on all of the, so now we have, on this machine we can run 12 different warps at the same time. So now it's going to run 12 iterations of this parallel for loop in parallel on different parts of this GPU. In fact, let's try to run that. Oh, but we need one more thing at least. There's this smallest. So by default, this is one of the many sort of confusing and relatively opaque aspects of OpenMP. The variable here, smallest, this is going to exist on the GPU. But that doesn't share memory with the CPU. So what happens? We're accessing the smallest. It starts out as 10 for some reason. So we can imagine copying that in. And in fact, since we're accessing these values, the compiler already sees both the values and the smallest. It sees that, oh, you're reading that. That means I need to get a copy of the values into the GPU, into this work group before we get going. So it'll do that automatically. But by default, it'll say, it's called first private. I think we discussed this briefly in the OpenMP discussion way back when, where you get the copy of the value, but after that it's private. So it just stays on the GPU. The number doesn't come back. So by default, the smallest value will stay on the GPU, and we will still see a 10 because it doesn't get exported back. So we have to tell it here. Map by default, when you map like this, it'll be read-write. Like it goes both directions. And you can also tell it, like, oh, I want it to only map out. So we only want to copy the values out to the device, but don't take it back. There's some other things we can tell it. Okay, so anyway, now we should be able to see the value of the smallest. Let's compile it. So that's kind of annoying. It took longer. But we kind of knew that, right? We tried this already with the long code. And we saw, well, that takes longer because we have to copy all the data in, and then we run this min thing on it. So, well, maybe that's not the end of the world. So now we know, at least, maybe we have an idea that that maybe it's not worth it. But measuring from here, unfortunately here we don't have the insight that we get with the direct OpenCL, so we can't see that, oh, it's the data upload that's taking time, right? Here it's kind of all hidden away, so we see, oh, it didn't go faster. Why? Not sure. Right. Yeah. It has to upload it every time, right? Mm-hmm. Why does it vary?
Computers.
I think if we had the code, we could probably, like if we have more detailed code, we could probably try to figure it out. And I'll talk a little bit about that sort of thing later on in class and next time as well. Okay, but anyway, it didn't run that fast, and we knew that this is because, yeah.
Oh, what happens if you have this SIMD?
Yeah, let's try that. Thank you. So what does it do? The SIMD says, not only do I want to run one thread on each warp, in fact, I want to run 32 work items on each warp. So now we should be doing the computation 32 times faster. But we know that it's not the computation that's limiting us. We have a problem with the upload. So let's see. Maybe it goes a little faster. Yeah, a little bit. Okay, so now we're actually using the GPU fully. And there was a nice little tool. What was it called? Maybe we'll try that too. Let's see. Oh. This is lines. What's it called then? Thought it was NVIDIA. Let's see. NVIDIA SMI. Oh, I must have just misspelled it. Okay, so this SMI says something about what the GPU is up to, although it's very little, but it's better than nothing. So at least we can verify. Let's try one more thing. I want to run with top as well. And we'll talk a little more about system-wide profiling and stuff later. But okay, so this program is cool, but you have to run it over and over. Here's another cool thing you can do. Ooh. So now it just runs it over and over. Just watch. Just runs the program over and over and starts from the top of the screen. Can be handy sometimes. It runs it every second now with a -N1. Okay, so we see that the GPU is only using 1 watt. It's kind of sleeping. It's not very hot. We have a utilization here, 0. No one's using it at the moment. Okay, so now we can try to run this program. Oh, and here we have, in fact, let me show all the CPUs. Yeah, so all the CPUs are pretty much idle. Okay, so let's run our program. We would expect, in this case, that the GPU is busy and maybe the CPU isn't. Actually, hard to tell, right? The upload is probably a big deal. So we probably are going to see both of them being busy. Let's see. Okay, so we have, oh, I went a little too fast. Did it run that fast before? Yeah, I get. Oh, that was a lot faster than before, yeah. Okay, but now it's sort of. Am I running the right program here? Yeah, I think so. That's really funny.
Now it's faster?
Yeah, it got a little faster when we have this thing going.
Now it's faster than just the CPU, isn't it?
I don't know about that. We can check that in a little bit. Okay, so now I'm just running it over and over, and let's see what it's doing. This is the one with the target. It's not using the GPU at all. Right? I guess it's just uploading, right? So that maybe can give us a little bit of a hint. I want to try another program that's really CPU, that compute heavy instead, just so we can see the contrast between the two. So we have one CPU being busy, kind of busy, and for the rest, the GPU isn't doing much. Maybe it's not that surprising. The computation itself, perhaps, well, actually, I don't know. I would think we should get more. Oh, we caught it. Ah, that's the thing. Okay, so it's running relatively infrequently. Why don't we run a little more often?
There it is.
So every now and then, spot it. Okay, good. Okay, so at least we can see it doing something. That's nice. And let's see if we can. Okay, I'll just hold in space here. Okay. Yeah. So anyway, almost all of the time, as we know from before, is being spent uploading this array. So let's get away from that program and do something different, just for comparison purposes. Let me see. Okay, so here's another program. This program checks if the number passed in on the command line is a prime number. Factorization, that's cool. Of course, it doesn't need a whole lot of memory, right? Pass one number and do really a lot of computing to see if there's a factor. There's clever ways to do factorization, but let's not worry about that. In this case, we're going to try to divide or take the mod. We have a number passed in, take a mod every number between 2 and the square root of the number, right? And see if it's 0. Well, then we know it's a factor. There's no point in going all the way up. That's going to take forever. I'm being a little clever here. Okay, so this is the factorization job, right? Run between 2 and the root. If there's no remainder, that means the number we had was a factor. And this is going to compute the max, right? The largest factor between 2 and the root. That's okay. Okay, so let me compile that. Yeah. Oh, that's handy too. That's right. So, of course, this sort of thing doesn't take very long. Small numbers. Now we're running it on the CPU, so still doesn't take very long. But we're reaching 1 million cycles, 6 million cycles. Maybe now it's starting to get a little bothersome. So maybe a little more. I'm using longs. I don't know how many decimal digits you get to use. Now I added 2 more. That's 100 times more. Maybe that's too much. But it's a square root, so it should be 10 times more. Okay. Oh, that's not too bad. All right. So 39 billion cycles. Cool. Let's run it with time. In fact, let's just count it down a little bit. And so now we see, we're using everything we're running everything on the CPU. That's awesome. This seems like a good compromise. All right. So see if we can do this with OpenMP. We take the incantation from previous one. I'm going to have to update it a little bit. We're basically just interested in this loop here. I guess we want the largest factor. And then let me drop the SIMD for now. Okay, so that should be it, which is really nice. I think OpenMP is not a language. It's horrible. It hides everything. But on the other hand, that's great. One line. So I can see when you're a domain scientist, like you're working on some, I don't know, weather simulation, and you have the choice between this and this other garbage that we saw last time, then probably you're going to go with this, even though you have no idea what it's doing. Because you don't have any idea what it's doing anyway, because you're a weather scientist, not a computer programmer, right? So that's fine. I think it's a good tool, but I wish there was a really great low-level language that actually knew about things like this, like GPU targets and SIMD and so on, better than C does. All right, one of you will have to do it. Like take the compiler class and then come up with a new language, please.
You've got some years on us. I think it's.
What's that?
We're gonna put that on you, and then you got a couple of years on us.
Okay. Well, we can do it together. There's the PhD program. Okay, so what are we doing? Yeah, let's just run this thing. Same parameters. Uh-oh. GPU disappointing us again, right? It's about the same time as the CPU. But, okay, so first of all, I guess, what's going on here? We got the right factor, that's good. But why is it taking so long? Seeing a couple things here. Taking quite a while on the system. That's good. We would expect that, I think. That's the GPU working. We're not spending time on the CPU. Why are we spending so much time in user land? Maybe there's a busy poll in there somewhere. Maybe we did something wrong. Maybe we have too many work items here that we're passing into the GPU because they don't fit on the GPU. I don't know. We're being too busy on the user. Okay. What would we expect from this? Like, what are we doing actually? The job is modulo, right? We know modulo is slow. Right? The latency of modulo was like 120 cycles or something on the Xeon. We don't know how long it is on the GPU, but it's still going to be slow. Maybe it's worse. That's the latency though, and these are all independent. Right? The divisions themselves have nothing to do with it. So on the Xeon, we have I think the reciprocal throughput was like 1 per cycle or something like that, pretty close, maybe a couple. Oh, okay, no, a couple cycles per. Because they're all independent, they can all run together. They're all in this out of order execution window. They're not actually out of order here, but they all run at the same time through pipelining in the divider. So we should be getting one of these every few cycles, right? So how many are we doing? Let's see. Let's just take about half. So 200 million of them. So on the CPU, it shouldn't take that long. Let's see, 200 million. One would expect way less than a second. How long did it take on the second? On the GPU? It was about 5. Okay, that's interesting. I'll have to profile that at some point. On the GPU though, how much faster should it go? Well, so far we only told it to do 1 thread per warp. And so there's 12 warps at the same time running. So we should get a 12 times speed up, right? But on the other hand, what's that?
Minus the upload.
Minus the upload, but there's no upload. There's uploading 1 integer here. Although there's a decent chance that we're maybe compiling the program in there, so there's a little upload for that too, but still it's going to be very minimal. But minus a couple other things. These GPUs are not nearly as clever as a CPU. There's no out-of-order execution, no speculative anything, and the clock frequency is lower. So say we lose a factor of 2 on the fact that it's a dumb processor. And then maybe we lose a factor of 2 on the clock frequency going from 2.2 to 1 gigahertz. Now we already lost factor 4, and so there's only factor 3 left. And I could be off by a factor 10 here in my guesses. So I guess it didn't really work out. Let's see if we ask it to actually use this for loop in a GPU way. So with SIMD, now it knows that we are running in SIMD style on this GPU. Right? So we're going to run on each warp. We will put 32 work items. And so ideally, we should get about a 32 times speed up. Is it? Let's see. 16 billion versus 2 billion. Well, it's not a 32 times speed up, but it's not bad. 8 times. Okay, so that seems, now it seems like we're in pretty good shape. Looks like we got a huge win here in userland. Is the work queue. There is a work queue one way or another in OpenMP. Right? There's no work queue in the same way in OpenCL. Right? That's not sort of the same model, but there's probably some overhead in managing the OpenMP work queue here that's hidden from us. And then the execution itself also sped up by a factor of 4. Right? It seems like this this userland overhead was the main thing. So we actually cut it down. Oh, maybe we can see here. Yeah, that's a 5. That's a 25 times speed up almost in terms of userland overhead. This is not that we did other things on the GPU. We did other things on the CPU. In any case, that gave us a pretty nice end result for one line of code. And about 2 hours of compiling. Compiling GCC, that's a big one. But you only do it once. So. There are some apt-get packages you can download. They don't work. At least I had the compiler crashing with null pointer exceptions. It's not good. But there was a nice little, in fact, I have a URL for, in case anyone wants to experiment with this. This was fantastic. Let's see, where is it? Yeah. So some guy put this together. Here's the script. Just run it. And it just works immediately. That's awesome.
Go set up the outset.
Yeah. Okay, but you do have to have an NVIDIA GPU to do it. Okay. Let's see, was there? I think we're pretty much done with all that. So that is going to have to wrap up our GPU discussion, I think. There's a lot more we can do. In particular, I'd be very interested in trying to learn more about the inner details, about what makes a GPU program fast and slow, and how to properly profile it. You'd have to go, I think, into the driver level of the NVIDIA driver. That one isn't open source. I don't know if there are any open source drivers for GPUs, actually. So that would be quite a challenge. The best approach would be to do an internship at NVIDIA, which is definitely within reach for anyone who finds this really interesting. They're always looking for good people. Okay, so now I want to take a step back and kind of look at overall system performance again. We've spent a lot of time on these various models of concurrent programming, and it can get arbitrarily nitty-gritty. Usually, the performance of your system probably doesn't depend on hand tweaking SIMD sort of vectorized code. Probably there's something else going on. Almost all the time, your program runs slow, and with some relatively simple measurements, we can figure out why. So, lest you forget what we talked about in the beginning of the semester, let's take another look at that and see how we can try to diagnose system performance a little bit. I found some cool new tools too that we can play with. Okay, so Let's call this optimizing program performance. So there's a couple of rules of optimization. All right. I don't know if you've seen these. First one is don't. All right. Generally speaking, don't, or don't yet. Right? You certainly want to wait with optimizing until you've tested everything, until you profiled it, until you really know this is the program you want. There was a guy called Donald Knuth. He said that we should forget about small efficiencies 97% of the time. Premature, and you may have heard this one. Optimization is the root of all evil. Exactly. Right. I think this is a very important point to remember. It's really easy to spend time. You're writing some program, you think, oh yeah, this actually isn't going to run that fast, right? This function that I'm working on, it won't run that fast. I should write it in a more clever way so it'll run fast. But then it turns out that nobody actually uses your function, right? Or if they do, they only do it very rarely. And so the total program performance change as a result of your optimization of this one function that converts a string into a floating point number, let's say, it's nil. There was no difference. And you spent a day doing it. There was another nice quote. This is not by a programmer. Voltaire said, "The best is the enemy of the good." Right? Point being, you can try to make the best of one little thing, and you'll spend a lot of time on that, or you can do a lot of good with all that time. Right? So all of these little kind of pithy quotes, the point is, let's profile first. Right? The 90-20 law of software development says 90% of the execution is spent in 10% of the code. Let's not call this the law. Let's call this the rule of thumb. Right? So first of all, we need to know which 10% it is. And we can't know that until we've finished writing the program. We know what it's supposed to do. Ideally, you guys, all of you, don't write programs. Right? Ideally, there's a whole army of other people writing programs, and you are the high-paid, like in the special corner room person who finds that 1% of code that really needs fixing, and you make it damn fast and save the company millions of dollars. Right? That's where you want to be. It's not clear. Not everyone cares that much about performance, but it's better than writing bookkeeping software for a living. Right? Okay. So another way to put this is profile first. Always profile first. But it's not clear that it's just your program that's running slow either. Right? Maybe it's not your program's fault. Or maybe there's other circumstances at least that affect your program. So I guess the first step is we have to have some rough idea of how we think a program should run. And then if it doesn't run as fast as we think it should, then we start looking into what could be going on. For a large program, it's not easy to just read the code and find out. And even profiling it doesn't necessarily tell you the whole truth. So there's some other steps that we can follow that will help a little bit. So I think first of all, we should figure out what is the system doing. We're running this program. Maybe the computer is doing other things too. Your program isn't running fast enough. Could it be that there's something is going on the system? So there's a bunch of resources on any given system that could affect program performance, and they're relatively easy to take at least a quick look at. So maybe start with that. So let's see. There would be utilization for each resource. Check. Utilization. So if it's CPU bound, what utilization would be, what's the percentage of CPU that's in use? In fact, let me write down a few different pieces, and then we'll go into details on each. Utilization, and then we have saturation, which is a slightly different concept, and then errors, which may or may not apply. Okay, so let's see what are some resources that are particularly interesting. CPU naturally, memory probably, I/O. This could be disk, reading from disk, or it could be network traffic, this sort of thing. And then you can get into much more fine-grained measurements if you want. You could look at bandwidth on the QPI link on the CPU. You could look at memory bandwidth, look at temperature, and all sorts. In fact, maybe that should even fall under error temperature. But anyway, these, I think, let's put these as the most important resources. So what does utilization mean for CPU? That is, what percentage of the time was the CPU running useful code? The CPU is always running something, always doing something. Well, maybe that's not strictly true. CPU can sort of take a break. There's a halt instruction where it stops doing anything. It doesn't come back until there's an interrupt. But utilization is fraction of time executing programs. Call that percentage maybe. Okay, so how can we measure percentage utilization of our CPU? It's a good tool. Come on, you used it. Top. All right. Top is cool. In fact, at least on most of the tops I've used, you can hit the number 1 and you see utilization for all of the CPUs separately, which I find more informative because on a single-threaded program, who cares, right, about this? If I run a single-threaded program full tilt, it's a 32nd of the machine, right? So it's 3% CPU utilization. Yeah.
Is there a reason you would use top over HTOP?
I know, it's just like I'm used to it. Top is fine. HTOP is great too. But you want to see the utilization for each CPU, because then you can tell that, oh, it's actually running 100% on one of them and all the other ones are idle. It's because we have a single-threaded program. That already tells us something about our program. Right? Probably, if we want to go any faster, okay, so well, maybe there's two pieces here. You could have 100% utilization and your program isn't running, right? Then some other program is using up the CPU. But if you have multiple CPUs, either you have a broken scheduler or, and you don't, it's almost never the case.
the other day I was noticing something while running and stuff. The same program, it shifts the code which it runs.
Why would it do that? Yeah, that's a good question. So on a machine that isn't loaded, I don't have a good answer. But if you have programs running on, like several programs running on different cores, then every few seconds there's a sort of higher level load balancing scheduler that kicks in and says, oh, this CPU is high utilization, this one's 0. Let me move a few processes over. So the CPU scheduler typically will always be per CPU. So there's just a list of, oh, these are the threads that I want to run now, that need to be run. And it's not all of the threads in the system. They have separate run queues like this because the coordination for the queue, all that synchronization slows down the system. And so then at a lower frequency, you have this higher level scheduler that just kind of moves things around to try to make it even over a longer term. But maybe that's what you run into. It could perhaps be that if you have a if there's just one process running, really, there may still be a benefit to moving it around, because if you run the core at full temperature, at full speed, it reaches a high temperature, and then at some point it has to slow down because it's too hot. So thermal throttling is what it's called. And so if you move between cores, maybe, or if you move between sockets in particular, you might see an effect there. I don't know if Linux is clever enough to do that. Right. Okay, so of course with top you can also see whether your program is using all of the CPU. But if it turns out that your program is not using all the CPU, it's just a lot of other things and all the CPUs are full, well, then I think we know what's going on already. All right, so then we don't need to be optimizing our program, we need to be buying a new computer or moving some things away. So very easy fix there. Okay, what about memory? Something similar. You can get a reasonable idea over here. I think what's really important is here, the swap. Let's see. Well, maybe let's see what htop has to show. Nothing. See, this is useless. I'm sure if you know which key to press, you can get all the details you want. htop, I'm sure, is fine. But anyway, a key statistic is how much memory is free and whether we're using any swap. Usually it would be showing page ins and page outs. I don't see this one at the moment. Maybe. Anyway, that's a critical problem. So if we have no free memory and we have no memory here in buffers and cache, that's actually memory held by the kernel for convenience. It's not something that's actively used. So if both of those are empty, then the only other choice is to start taking some pages of memory and writing it out to disk so that you can reclaim the memory for now. And then later on, when someone wants to access that memory, well, then we have to go to disk, read it in, but before that we have to evict something else to disk. This whole thing is called swapping or thrashing sometimes, or anonymous paging is another term for it. And memory is incredibly faster than the disk. Disk probably at least 1 million times slower. So once you start having memory problems, that's a real killer. So this, just looking at overall memory utilization, not worrying about this. This is the same as free memory. It's a good other sort of top-level measurement. Right, okay. Free memory, including buffers. Okay. There's something similar. Oh. if you're running a database or anything that does disk access, generally speaking, I/O will be what limits you, and I/O top will tell you how much time you're spending talking to the disk. Of course, we're not doing anything particularly interesting at the moment, but this is definitely important. Here, if you're seeing a lot of swap in traffic, that means you're low on memory, probably, and for the rest, it's just like the program wanted to read or write. And that can really slow down your program. So I/O top, I think there was a percentage in there. Yeah, so here, this is probably out of the total available I/O capacity utilization. Okay. Saturation is something slightly different. You know, utilization isn't really bad. If you have 100% utilization, as long as you're not going over 100%, everyone's happy. Right? You have this, say, an Apache file server or Apache web server. It's loading pages for people, and whenever a request comes in, it's ready to serve. Right? But it's well timed, so you're basically hitting 100% utilization and still providing excellent service. So it doesn't have to be a bad thing, especially if you are I/O bound, like an Apache server would be limited by requests. If there are no requests, there's nothing to do. So there's another program called Uptime that says something different about CPU usage. So these are load averages. That's the length of the run queue, of the average run queue in this case. So we have 32 run queues, right, one per CPU. And what's the average length of these queues over different time periods? I forget which one is the longer time period. Maybe if we run it again, we can see. Probably this is short term, because it changed a lot, and the other ones changed just a little. Yeah. Right. So anything below 1 is great, because that means whenever you needed to run something, there was a CPU available. If you start seeing 3, 4, 10, then you have a real problem, because now, at least for a CPU-bound program, it holds the CPU for 10 milliseconds. So now if you have 4 people ahead of you in the line, you're going to wait 40 milliseconds for the CPU. This is just completely unacceptable. Okay, uptime's great. For memory, I think for memory we want to talk about probably swap utilization, and page ins, page outs. That's not really saturation here, but swap utilization, that's basically how much oversubscribed is the memory. If you start using swap, that means your programs asked for more memory than what was available in the system. Errors is more relevant for disk access, but there it's extremely relevant. See if we have a smart. No. Okay, I don't have it, and I don't remember the name. For disks in particular, they have a tendency to, after several years, a few sectors kind of stop working, and that's maybe okay, depending on the file system. But at least on a desktop drive, you'll find that it's sort of like with the CD, right? You get a scratch on the CD, and a DVD. It's trying to play a movie from a DVD. If you still do that, it kind of stops, and it tries again and again and again, right? And then after trying 100 times, it says couldn't do it, and then skips to the next chapter, right? Or next whatever in the movie. Same thing for a desktop drive. Sometimes it can continue forever, and that's a really bad idea. But if it doesn't have a copy of the contents of that sector, it'll just keep trying. Keep trying to read until it gets a read that passes a CRC checksum. There's a checksum on every sector. So you can imagine that even if you're not busy, like you're not doing a whole lot of I/O work, but you have one of those bad sectors in an important place, that would grind everything to a halt. The whole machine will just basically stop responding. And yeah, you can tell that from, it's called Smart Tools, something like that. The sort of standard that the hard drives provide, this interface for reporting sector problems. With ifconfig, you can also get drop packets. So if we're doing something, now we're talking distributed systems here, but if you're doing networking, drop packets are horrible. Like they're much worse than having a high ping time. Having a drop packet, that can really get you in trouble. Okay, so those would be typical errors. Bad sectors. And network packets. If you have a bad CPU, a CPU that doesn't always jump when it should jump, that's not going to work. Right? There's no point in trying to look for such errors because you could never run a program on that CPU. So don't worry about that. Memory can be bad. I don't think that would cause performance problems. That would also crash your machine pretty quickly. Okay, so I think that's the sort of the high level on the system. So now, if we've determined where we're going wrong, and probably if we're, for the purpose of this class, we probably have a problem with CPU utilization. Right. So now we want to see. Actually, maybe we have two different possibilities here. One is our program is using the CPU all the time, in which case we probably need to figure out some way to optimize it. And the other one is the program is taking forever to run, but it's not using the CPU. That's also relatively common and quite a separate problem. Okay, so let's see. Oh yeah, I like this one. So this kind of summarizes the possible states of a process. Right? And we've spent almost all of our time here, right, in this class, figuring out how we can make it run faster when it's running. But if the program isn't actually running, how do we find out what it's doing? So first we need to know what are the possible things that it could be doing. If it's in a runnable state, so there's these are things that a process could be doing, right? All the blue ones. It's executing, it's just running instructions on the CPU the way you would expect. If it's in a runnable state, it's sitting in a queue waiting for the CPU. Why would it be waiting for the CPU? Well, someone else is using it. So that probably has to do with the resource utilization we just talked about. It could be doing this anonymous paging, is swapping. So you actually are on the CPU. This is the program is scheduled to run. It's running at the moment, except it has a page fault because whatever piece of memory it wanted to access isn't actually in memory. It's this virtual address space stuff. So you try to read an address, you put some stuff in there, but when you try to access the memory, the CPU triggers a page fault, the kernel takes over and decides whether you were actually allowed to access that address. So in that case, the kernel will have to find a victim, find some memory to write out to disk, find your stuff on disk and put it in the newly freed memory, and then put it back in the page table and then return to you. And all of that is you still running. Right? It's like kernel is executing on your behalf. It's doing work on your behalf. Your process is still, it hasn't been switched out. It's just running in supervisor mode at the moment. Of course, when it's reading from disk, it's going to get context switched, because reading from disk takes 5 milliseconds. And there's a lot we can do during 5 milliseconds on a CPU. All right, so getting that paging count with IOstat will kind of tell you if this is a common, no, IOtop will tell you if that's a common problem. A couple other things we could be doing here is we could be sleeping, waiting for I/O. Right. So if I try to read from a socket, from a network socket, or from a command line, or anything, my program isn't going to do anything until the I/O I was waiting for arrives. It's a very common problem. You have some high latency partner you're communicating with, and it turns out that your program is just waiting for them all the time. Maybe you should be doing other stuff in the background, but you didn't figure that out. Right? So in that case, we need to catch the problem and switch to asynchronous I/O perhaps, or a threaded programming model. Let's see, how can we find out that part? So, for example, why is this program taking so long to finish? Right? What does cat do? If you say cat file name, then it outputs the stuff in the file, right, on the command line. But what does this thing do? It's waiting for? It's not waiting for a file name.
It's just echoes.
Yeah, it's reading from standard in and then wants to write it out to standard out. That's all it's doing. I don't really know why you would do that. Oh, actually, yeah. So if you say like this, right, now it ended up in stuff. That's maybe why cat works in both directions. Okay, but anyway, so now it's reading from standard in and writing to standard out. So we happen to know that that's what's happening. But if we have a more complicated program, maybe we don't know what's like. Why does it keep stopping and not making any progress? How can we figure out what cat is doing without having the source code at this point? Or let me say, without trying to read the source code, right? Because it's millions of lines. We need to know, yeah, do you have an idea? No. There's lots of handy tools for this. Unfortunately, perf isn't going to help you. Right? Perf is a sampling thing. It samples the program that's on the CPU. This program is sitting in a queue waiting for I/O. So we'll never see it. Top isn't going to help you, right? Doesn't even show up. Maybe, oh, that was the wrong machine. That's maybe why too. PS could help. Let's see if we can find this cat. Okay, this is pretty good. So this state here, PS is nice. There's all processes running on the, there's lots of different ways to ask it, but basically, what are the processes that are running on the machine at the moment? And this state here says something about what it's doing. And for our cat, you see that it's sleeping. I don't know what the plus is for. So it's sleeping, that's good. So at least we know it's waiting for something. I think we need to do a little bit better. One handy trick is strace. So strace, now I'm attaching it to a process. You can just say strace and the process. It'll tell you all the system calls that the process is making. And in this case, wrong one, this one. There. That's the system call, right? So we're reading from, and we even know what we're reading from here, standard in. There we go. Let's try it a different way too. Right. So this tells us everything that cat was doing, well, with respect to the kernel. Can be very useful. Let's see. So sleepy processes strace is handy. Okay, so there were some other cool tools called off CPU time programs. We looked at that before. Basically, there are some programs for keeping track of what state programs are in and how long. And I think this guy Brendan Gregg had a really good collection of those. This, right? Highly recommend you take a look at that. Basically, you can't use a sampling profiler for anything like that because, well, it's just asleep. Okay, so what about if we are running a program that is doing something busy? Well, there's perfstat, which gives us see what it says. Oh, that's weird. Okay, right. Perfstat gives us some high-level statistics without any particular parameters passed. But what's really nice about perfstat is it gives you an exact count. So you tell it, oh, I want to know how many page faults were incurred. You just tell it, I want to count the event page fault. Perfstat. Right? 116 page faults happened during that time. This is not sampled. There's a count. So we just told the kernel, for this duration of this execution, we told the kernel to add a counter every time a page fault occurs. There's a piece of code that's now inserted into the kernel that tracks page faults. And then that piece of code disappears. Very clever stuff. That's the extended Berkeley packet filter stuff, eBPF. In any case, perfstat is excellent for getting a total picture of what happened, and you can also tell it with an interval. What is it? T. I forget. There's a parameter we can tell it to just do that every second, so you can get an overall picture of how many L1 cache misses were we incurring during this part of the execution of the program. Okay, we're out of time. We're going to go through a whole bunch of other tools like this and some examples next time. So I think next week is the last week. The rest of the class will be on Tuesday. We'll talk a lot more about various ways of profiling your program, trying to understand what the system is doing. And then on Thursday, we'll try to kind of review everything that we've talked about and have some discussion about the final exam. All right. Thank you, and have a good weekend.